Welcome to Sequences and Series for Pre-Calculus Math 11. We are looking at infinite geometric series, section 1.6. So infinity, what we're going to do here is we're going to use, we use the symbol infinity, which is actually just kind of a sideways 8, to represent infinity. And it turns out infinity is a somewhat large number. How large? Very large. So what we're doing is we're taking care of infinite geometric series. So we're talking about a geometric sum that we saw in the last podcast, but we want to see what happens when we add up basically infinitely many of these terms. So let's take a look at a few examples here. We have 3, 6, and 12 all added together. So term 1 is 3. That's our standard notation. The common ratio is 2. So if we're going to use the sum formula, where S sub n is term 1, 1 minus r to the n over 1 minus r, that should work out. Let's go with sum infinity. Let's replace n with infinitely many terms. We're looking for term 1, which is 3, 2 to the power infinity over 1 minus 2. The 1 minus 2 in the denominator, that's pretty easy. That's negative 1. Here is where it gets a little bit more conceptual. 2 to the power infinity. If we start raising 2 to a power and it gets bigger and bigger and bigger, what happens? Well, let's just start multiplying 2 times 2 times 2, basically infinitely many times. We are going to end up with a very large number. Let's call that large number infinity. 3 divided by negative 1 is negative 3. 1 minus infinity is basically negative infinity. And 3 times infinity is infinity. So we see that if we add up infinitely many numbers, we're going to end up with an infinite sized number, infinity. We could also say that this does not exist. Or use the letters D and E. Let's try this again. Term 1 is 16. Common ratio is 1/2. So let's go right away to the sum infinity formula. Term 1 is 16, 1 minus 1/2 to the power infinity over 1 minus 1/2. The 1 minus 1/2 in the denominator is 1/2. I'm going to break up this fraction. We know by power rules that we can break up the fraction into 1 to the power infinity over 2 to the power infinity. Let's do that as a first step. 16 divided by 1/2 leaves us with 32. 1 to the power infinity, if you raise 1 to any power, we still end up with 1. 2 to the power infinity, we know from the last example that that is infinity. So again, we're going to have to go into a little bit of a conceptual idea here. 1 divided by infinity, we have a number, 1, and we're dividing it up into infinitely many pieces. If we bring a pie and we cut it up into infinitely many pieces, how much pie do you have? Essentially 0. So this works out to be 32, which is actually kind of a strange number. So we have an infinitely long series. This series goes on forever. 16 plus 8 plus 4 plus 2 plus 1 plus 1/2 plus 1/4, etc. off to infinity, yet it only adds up to 32. Let's see why this happened. In this first example, because it is a growth series, how do I know it's a growth series? Is because common ratio is 2. The infinite sum, which the notation we use is S sub infinity, is undefined or infinite. In the second case, because it is a decay series, which means that the terms in the series are getting smaller. How do I know it's a decay series? Because the common ratio is in between -1 and 1. The infinite series, the infinite sum, which is S sub infinity, is finite. And what finite means is it's just a real number. So in this case, it was a finite number of 32. So you can have an infinite sum have a finite, an infinite series have a finite sum as long as it's a decay series. So the stipulation, the only way this works, is if our common ratio is a decay ratio in between -1 and 1. So let's see what happens here. Let's generalize. Sum infinity t1 1 minus r to the infinity over 1 minus r. If the r to the infinity here is based on a number between -1 and 1 being raised to the power infinity, that term should equal 0. And what we end up with is sum infinity equals basically just t1 over 1 minus r. And I'm going to put an IFF there, which stands for if and only if the common ratio is in between -1 and 1. So if the common ratio is not in between -1 and 1, what you can say is that the sum infinity does not exist, or the sum infinity equals infinity. If it is between -1 and 1, then we can just use this new little formula, S infinity equals t1 over 1 minus r. In class, we'll see a couple examples of this in real life, how an infinitely long series can add up to a finite sum. This ends the notes for Sequances and Series infinite series. What follows now is some examples.